formula. Change equals equilibrium minus initial. So only this guy, HI, has equilibrium, has initial. So therefore, for the change for HI, it will be 1.07 times 10 to the negative 3 minus 0 equals 1.07 times 10 to the negative 3. Okay. So once we have one change, so we put it here, we see positive 1.07 times 10 to the negative 3. So why emphasize positive? Because HI is a product. So at the beginning we have nothing, 0. Then at equilibrium we have something. So therefore this HI concentration increased. So if the product concentration increased, so then where the product come from? It comes from by consuming the reactant. So therefore the reactant concentration will decreases. So therefore the change for these two will be negative and negative. Okay? Then negative how much? We will use the coefficient ratio from the balanced equation to find those out. Okay? So therefore, let's see the change for this HI, we will use as the starting point. So this much change for this HI. So as what we did, well, we want to use the coefficient ratio as a conversion fraction to convert this number for HI into the number for H2 and I2. Let's start with find the number for the H2 first. Doesn't matter. So therefore, we want to cancel out the HI and get the H2. Then what are the numbers for HI? What are the numbers for H2? We'll use the coefficient in the balance equation. And let's go to look at the coefficient in the equation. So the equation is here. So the equation, if I highlight, is this one here. And then in this equation, we can see the coefficient for HI is 2. So therefore, we write 2 here. Okay? So now you know where the 2 come from. So the 2 come from the coefficient in this equation 2. Okay? And then let's see what is the coefficient for H2. So the coefficient for H2 is 1. 1 is omitted. So therefore, we write here 1. Okay? And then you can see the cancellation of the name HI cancel out with HI, so get H2. Then you just take the number, divide, you get 5.35 times 10 to the negative 4 more molarity H2. Okay? And we already decide the sign for H2 should be negative, so therefore we just write a number here in the table. So 5.35 times 10 to the negative 4. Now similarly do the calculation for I2. So we start with 1.07 times 10 to the negative 3 HI and over 1. Just anything divided by 1 still is the same things. And then here again we want to cancel out HI and get I2. So then similarly you go to the balance equation. So the coefficient for HI is 2, the coefficient for I2 is 1. So therefore go back to these fractions of 1 and 2. And then see the cancellation for the HI cancel out and we get I2. And the same number. So you take 1.07 divided by 2, you get 5.35 times 10 to the negative 4 molarity of I2. And we already know the I2 same as H2 has negative change, so therefore 5.35 times 10 to the negative 4. And then from this initial and change, you can find out equilibrium. So that means equilibrium concentration of partial pressure will equals the initial plus change. Okay? So therefore, if we use that H2 H2 concentration, if we write H2 concentration, okay, equilibrium equals initial plus change. And we use angle bracket means molarity H2, let's say at E, it will equals initial is 1.0010 to the negative 3. So that's the initial concentration for the H2. Then plus the change, which is negative 5.35 times 10 to the negative 4. So therefore, you put these two numbers together and you get 4.65 times 10 to the negative 4 capital M. And then the change for I2, do a similar calculation. I2 at equilibrium will equals initial plus change. So for I2 initial is 2.000 times 10 to the negative 3. The same amount of change, negative 5.35 times 10 to the negative 4. So that gives us 1.465 times 10 to the negative 3, capital M. Okay? So we'll write those two numbers in the table. So this number become 4.65 times 10 to the negative 4, 1.465 times 10 to the negative 3. Right, now we have all the three concentrations at equilibrium. So this at equilibrium, this at equilibrium, this at equilibrium. And you want to find the Kc. So then it's simple. So just substitute those numbers into the equation for Kc. So let's see what will be the equation for Kc. So let's see for this problem for Kc, just write the equation for Kc, right? So adding the first two problems, and if the given the equation, you have the Hi as the product, so therefore Hi concentration and square divided by the concentration of H2 divided by the concentration of I2. So those should be all at equilibrium. So then you plug those numbers in at equilibrium. 1.07 times 10 to the negative 3, this should be squared, divided by 4.65 times 10 to the negative 4, no square, but that should multiply by the concentration for I2, which is 1.465 times 10 to the negative 3. And then you just put those numbers in your calculator, you get 1.68. So the answer is C. Okay, so next question is the question number 7. Okay, so give you some moles of that equation, that reaction. So give some mole of Hi, some mole of H2, some mole of I2. Give you the volume. Okay, this is the volume of the container. Then also give you the Kc. So this is the Kc. So you want to predict if this mixture at equilibrium, if they are not, which direction the reaction will proceed. Okay. So to find out the direction in which the reaction shall proceed, we compare the reaction quotient Q with the equilibrium constant K. So Q has the same expression as the K, except when calculating Q, we can use any concentration or partial pressure, whereas when calculating K, we must use concentrations or partial pressures at equilibrium. Okay. So for this given problem, we are given the Kc. So we need to calculate QC to compare. And so therefore, we need to calculate molarity from the given moles and volume. Okay? So let's calculate what is the molarity of the given information for the Hi. So that will equals mole of HI divided by the volume of the container in liters, which become like kind of the solution's volume. So the mole of HI, let's say, is 2.0 times 10 to the negative 2 HI mole, and divided by 2.00 liters. So that'll give us 1.0 times 10 to the negative 2 moles. And then we'll do a similar for the other two, right? So we have the moles of let's say the H2. So we have H2. The mole of H2 is 2.5 times 10 to the negative 2 mole of H2 divided by 2.00 liters, so end up 1.25 times 10 to the negative 2 capital M of H2. And similarly for the I2. So I2 will equals mole of I2, which is 3.0 times 10 to the negative 2 mole I2 divided by 2.00 liters equals 1.5 times 10 to the negative 2 capital M I2. Alright, so we said that Q and K have the same expression. So for this given problem, so our QC will equals the HI concentration, which is the products on the top, divided by the concentration of H2, and then divided by the concentration of I2. So we'll plug those numbers for this mixture. We don't know equilibrium or not. So we calculated the HI concentration, which is 1.0 times 10 to the negative 2, and we need to square that. Then divided by H2 is 1.25 times 10 to the negative 2. Then times I2, 1.5 times 10 to the negative 2. Okay, so you multiply and divide. So you get 0.533. And obviously, so Kc is 50.5. So 0.533 is smaller than 50.5, and this is the QC, this is the Kc, so therefore QC smaller than or less than Kc. So therefore, you can think about that picture. So if this is the Q and this is the K, so if Q equal to K, then is equilibrium, right? If Q equal to K, so at equilibrium. And one problem is if you have that picture like this. So let's say this is the Q, and then this is K. So in this picture, Q larger than K, and so here we are not thinking about to change the temperature. So the K only depends on temperature. So therefore we will keep K as constant. So therefore for this situation, it's not equilibrium, and you want to reach into the equilibrium, you want to reduce Q. So reduce Q, and we know Q has the products on the top, so therefore we want to reduce the amount of products. And so in the same time, we increase the amount of reactant. So therefore this means if Q larger than K, so our reaction should shift to left, to proceed to from right to left to get equilibrium. Okay. Now for our problem, for our question, this question, we have this picture. So this is the Q, then this is the K. So in this picture, we can see Q smaller than K. So again, we keep K constant, and we want to change Q to make these two equal, so therefore we have to increase the Q. So then you see what is the Q looks like. So Q has product on top. So if you want to increase the Q, that means you want to increase the product or decrease the reactant. So therefore for this picture, so our reaction shift to right to reaching equilibrium. Okay? So therefore the only choice that matching this problem, okay, is answer D. Okay, so question number 8. Which of the following statement correctly describe what will happen to the direction of the reaction if the size of container change? Okay. So here are the summary about the volume change. For reactions involves gases, if the sum of the coefficients of the gaseous reactant and the sum of the coefficients of the gaseous product are different, then the change in volume will shifts the position of the equilibrium. Okay? So what this means is you examine the given equation and then see who are gaseous. So in this problem, this product is gaseous and both reactants are gaseous. So then the sum of the coefficient of the gaseous reactant. So in this problem, your sum of gaseous reactants will equals 1 from the gaseous H2. So the coefficient for H2 is 1. So therefore, we see the coefficient for one gaseous reactant is 1. You want to find out the sum of the gaseous reactant, let's say coefficient. Right? So one gaseous reactant coefficient is 1. Then sum means add. You add the coefficient of the other reactant or reactants. So we have other reactant in the I2 gas. So also have coefficient 1. So plus 1. So therefore, the sum of the coefficient of all the gaseous reactants is 2. And then let's see what is the sum. What is the sum of the gaseous product coefficient? Well, there is only one product which the HI coefficient is 2. So therefore, the 2. Okay. So that's how you get the sum of the coefficient of the gaseous reactant or the product. Okay. So if they are different, then you use this guiding line. Increase the volume while shifting the equation to the side with a larger sum of the coefficient of the gaseous substance, and decreases while shifting the equilibrium to the side with a smaller sum of the coefficient of the gaseous substance. If the sum of the coefficient for the gaseous reactant and the sum of the coefficient for the gaseous product are the same, then the volume change has no effect on the position of the equilibrium. Okay? So, because for our chemical reaction for this H2, for our chemical reaction for the H2, for one H2 gas plus one I2 gas produce 2 HI gas. So the sum of coefficient. Okay, for this rectangle, 1 plus 1 equals 2, and then the sum of the coefficient for the product is also 2 plus 0 is also 2. So 2 equals 2. Okay? So for this reaction, volume change has no effect on the equilibrium. Okay, let's see one example that has no effect. Okay, so if I give the Haber process, let's see another problem or example, the Haber process. So we have N2 gas plus 3 H2 gas produce 2 NH3 gas. And this one, let's see what is the sum of the coefficient of gases. So here's 1, here's 3, so 1 plus 3 is 4, and here's 2, so therefore is 2. So now you compare 2 and 4. Okay? So the left side has more gases, the right side has less gases. So therefore, one example is increase volume will shift our equilibrium to the left. Okay? And oppositely, if you decrease the volume of this reaction, you're going to shift it to the right. Okay, so next question, number 9. So at this 500 K, the reaction this has Kp this. In an equilibrium mixture at 500 K, the partial pressure of NO is this, partial pressure this. Then what is the partial pressure of NaCl in this equilibrium mixture? So this question is give you the partial pressure at equilibrium of all the substance except one. Also give the Kp. You want to find out the equilibrium concentration for that one that is missing. You first just write out the Kp for this given equation. So as usual, you will write the product on the top. So product NaCl has a coefficient 2, which is the gas, so should be in the equation, so square. Actually here all are gases, so therefore the other reactant will be NO has a coefficient 2 and raised to the power 2. Then we have another reactant Cl2 has a coefficient 1. Alright. So you know when you write Kp or Kc, you know those numbers should be at equilibrium. Okay? So now you have, let's say you list out, so you have Kp give to you 51. And let's see the partial pressure of PNO, so then at equilibrium, so PNO at equilibrium equals 0.325 atm. Okay? And then partial pressure of Cl2 at equilibrium equals 0.165 atm. Okay? So this number we know. So Kp 51. This number we know. This number we know. We don't know that number. So P NOCl is a question mark. So I just substitute or plug in those numbers. So get 51 equals P NOCl squared, P NOCl squared divided by 0.325 squared and divided by 0.165. Okay, so we can solve this equation. So solve for P NOCl. 51 times 0.325 squared times 0.165 equals P NOCl squared. And this few number multiply, we get this number. Then we take the square root. This equals P NOCl. So that's 943 ATM equals P NOCl at equilibrium. Okay, so therefore this will matching the answer E. Or if we keep 2 sig fig, so that will equals 0.94 ATM. 0.94 ATM. Okay, so question number 10. Given at 1.000 liter flask filled with 1.000 mole of H2, 2.00 mole of I2 at this temperature, give you Kc this, then what are the equilibrium concentration of HI? Okay, so we need to use IC table to find the expression for the equilibrium concentration. So we will find the expression, maybe not the number yet. Then we will use the Kc, set up the equation and solving a quadratic formula. So therefore, we need to first find out molarity for the given moles and the volume. Okay, so we write, let's see, the initial, right? So field, and we can see this will be the initial H2, it should be mole of H2 divided by liter initial. Okay. Initial, that means you fill the container with. So 1.00 moles of H2 and the volume 1.000 liter. So end up with okay, so the other one is I2, also initial. So that will become more of I2 initial divided by liters. So initial I2 is 2.00 mole of I2. Again, same volume. So that become 2.000 mole of I2. So by imply the HI initial is 0 molarity. Okay. Now the IC table. So we have H2 gas plus I2 gas produce 2HI gas. Okay, so let's make the IC table. I C and E. Okay, initially this is 1.000, this is 2.000, and then this is 0. Okay, so now